a 17C video about directional derivatives. So we're going to find the directional derivative of the function of xy equal to x cubed y to the fourth minus y cubed at the point 1, 2 in the direction of this vector. So first I found the gradient, which is just the partials. So the gradient is 3x squared y to the fourth, right, the partial with respect to x, and then 4x cubed y cubed minus 3y squared, the partial with respect to y. Evaluated the point we were actually moving from, right, because again, we're talking about if you move in this direction from this point, what's the slope of the surface? So plugging in 1 and 2 for x and y, we get 3 times 1 times 2 to the fourth, which is 48. Plugging in 1 and 2, we get 4 times 1 times 2 cubed is 8, minus 3 times 2 squared is 4. So we get 4 times 1 times 8, minus 3 times 4, which is 32, minus 12, which is 20. Okay. So then, to find the gradient, to find the directional derivative, we do the gradient dotted with the directional derivative, which is just the gradient 48, 20, dotted with 12. 48 times 5 is, I just multiply by 5 and do times 10 divided by 2, so 480 divided by 2 is 240, plus 20 times 12 is also 240, kind of a coincidence there. So our directional derivative, but I forgot something, right? If I'm in the direction of u, u needs to be a unit vector, so I actually really need to divide by the magnitude of u. So you need to divide by the square root of 5 squared plus 12 squared. That's the square root of 25 plus 144. That's 169 squared. 169 is 13. Should be 480 over 13. Still a big number, but not as big as it would be. So it's a very, very steep slope. So if you're at that point moving in that direction on this surface, you are going up at a very, very steep slope. I just caught my hair in the background. My hair looks super funky in the back. Oh well, that's how it is. Okay, but then there was this question, I think this is like the first, similar to the first question of Rademacher's homework. Find the directional derivative of the same function at the same point. But now in the direction of pi over 3. And I was making a mistake when I actually recorded another video that I deleted because I was like doing this the wrong way. I was making the wrong assumption that pi over 3 was the angle between the vector. I was making a wrong assumption. I was trying to calculate the dot product doing this, where the dot product is the gradient, the magnitude of the gradient times the magnitude of the vector times cosine of the angle between them. And the mistake I was making is assuming that pi over 3 was the angle between the gradient direction and the vector u, because it's not. What the question's actually asking is to find the directional derivative in the direction of pi over 3. We don't know what direction the gradient's actually in. We could find it, but that's not really the point. So we're going to do the same sort of way. We're going to do the dot product of the gradient of the gradient of dotted with u. Gradient f is the same as it was before. It's 48, 20. And the direction of u, the vector u, well, if you're going in the angle pi over 3, you're thinking, okay, well, here is the angle 0. There's the angle pi over 3. This vector should have a length of 1. So then the x coordinate is just cosine of pi over 3. The y coordinate is just sine of pi over 3. So the vector that u is represented by is the vector 1/2 and root 3 over 2. So that's what we're going to have to dot it with there. And then when we multiply together, 48 times 1/2 is 24. 20 times root 3 over 2 is 10 root 3, and that's it. So if you're just given an angle as your direction, you need to turn that angle into the unit vector. So whatever your angle is, so if we're in the, so key point here, if the direction is just given by some angle theta, then the vector u, that's the unit vector, is just the vector cosine of theta sine theta. That'll always work. So that's how you tackle that problem for Rademacher's first homework problem.